We have studied the sensitivity and optimization study of this cylindrical pressure vessel with spherical end closures, and for that we used a 2D axisymmetric representation. So the original geometry was a 3D solid based on a simple revolve operation, and that was again based on this cross section. So internal radius was 100 millimeters, and the spherical portion is also got an internal radius of 100 in here, and the thickness was defined as 4 millimeters, and we made that thickness a parameter so that it's a relation driven dimension. So that helped us in the Creo simulation sensitivity and optimization studies. Now what we are going to do is try to represent this using a shell idealization, and for that we'll first create a mid-plane surface. So we'll need to pass a simple line going through the mid section. So if this is say 4 millimeters, so we need to pass a line through the middle of this shell thickness, and also respecting that the internal radius has got to be 100 millimeters. So I'll start a new model, so let's cancel this and then file, new, and then it will be a, let's say, PV1 shell 1, and I can do this in any plane I wanted, because it is going to be a 3D model, and 2D axisymmetric models were limited to the XY plane, but 3D shell models can be done on any plane. Well, anyway, let's start on the XY plane, and I want to create a revolve operation on that. So I can create a line that's representing the mid plane or mid surface of the cylindrical portion, and I can change to construction mode to help me construct the spherical portion. So I can click on that and make sure I hit the revolve axis, so I can go back out of the construction mode. So I can create an arc. The center is at this point, and starting from the end of the cylindrical bit and ending at the rotation line, revolve line. So we can say OK to that, middle button on the mouse, and then identify our dimensions. The main dimension that was 150 millimeters, and the other dimension was the internal radius. Well, this is 100 millimeters, but we are going to define it as a shell model, so this is going to be the middle of the shell. So we need to make sure that on top of 100 millimeters we can add half of that thickness. So the thickness value we'll need to define as a parameter, and then we can refine the dimension here. So we can just keep it like this at the moment, and then complete our revolve operation. It just says that there is no solid geometry in the model to intersect with this feature, so sketch must be closed. If you continue, it will change automatically to a surface, which is fine because that's what I wanted to do, and I need to revolve this around y-axis, so this creates a surface that is representative of this pressure vessel mid-plane. So I can then go back to my model intent and specify a thickness parameter. And in the past I used thickness 1, so I can just say add thickness 1, and let's say initial value is 10 millimeters. OK. One important thing I need to ensure is that I have used the correct model properties, and I need to change the units to millimeters Newton seconds. Set that. I need to interpret the dimensions, so 1 inch becomes 1 millimeters. So close that, and also assign a material property, which is going to be low carbon steel. So close that, and now I can ensure that the calculation of the mass, etc., will be done using the correct set of units. So this geometry is the mid-plane of the pressure vessel, and I've defined a thickness, and if I go back to my Simulate application, I can define this as a shell. So that will be done under shell, and shell properties, etc., can be entered here. But instead of working on this sort of half model, it will be beneficial to define maybe a 90-degree segment of this, and I can achieve that easily in Creo Parametric. So if I can cancel that and close Creo Simulate, if I go back to my Revolve Operation, I can edit that so that it's only revolving 90 degrees. So if I OK that, and that's my 90-degree revolution of this shell, press OK, and now I can go back to my Creo Simulate and identify my displacement and other pressure boundary conditions, etc. The first one to do here is identify shells, and they are going to be essentially these two surfaces, and these purple arrows indicate the shell normals or the surface normals. So if we can keep that, that's okay. Initially, the thickness will be also identified as the parameter. So I've defined my thickness 1 here. The part material is steel low carbon, and OK that. And we can see that the 10 millimeter thickness is added on either side of this mid plane, and that is the shell definition. Quite straightforward to generate. And we can also now ensure our sketch was done accurately. So if we go back to our sketch, that sketch was done at an internal radius of 100 millimeters for the cylindrical portion and also for the start of the spherical portion. Now if we added 10 millimeters of thickness on either side of this line, which is representing the mid-plane, the actual inside radius of this vessel would be 95 millimeters. So what I can do is add the half thickness to my internal radius. So I can do 100 plus thickness 1 divided by 2, so that is adding half of the thickness to the internal radius, and I can enter that, and it will replace the number defining the internal radius with this relation 100 plus thickness 1 over 2. Let's say yes, so that immediately goes to 105 for the internal radius of this particular line. And if I now look at my surface, that is at mid-plane of 105 millimeters. And if I now go to Simulate, I can see that my shell definition, the internal radius of the shell will start from 100, and the thickness is now defined as 10, so outside radius is going to be 110. Now we can apply some boundary conditions on these before we solve this. The displacement boundary conditions can be applied on edges of the shell. So click on edges, and on this edge and this edge, what I can say is that on this edge, this is a symmetry boundary condition. So I know that on the x-axis, this edge should not move. So I can fix it in x, but leave it free in y and z. And another thing to do with these shell models is to make sure the correct rotations are fixed. So for the surface, which is on the YZ plane, I need to make sure that the rotations on YZ are fixed and rotations in X are free. So that's my symmetry boundary condition. Press OK for that. And I need to do similar on the other face. Click on displacement, click on edges and curves, select this line and this line, and on those two lines, so if you look at which plane these lines are on, that's the XY plane, I need to make sure that the points on these lines are fixed in the Z direction. So in terms of translation, they are fixed in Z. In terms of rotation, I need to make sure they are free to rotate in Z, but fixed in the X and Y. So fix X, Y, and free Z for the rotations. Press OK to that. So these are my symmetry boundary conditions on these two edges of the shell, and the final displacement boundary condition is on this edge. So click on edges and curves, click on this line. So on this line, because this line is on the XZ plane, I need to make sure that the Y displacements on this line are fixed. So I'll need to free X and Z. X and Z, if you recognize, are also corresponding to radial directions. So when I pressurize this vessel, it should be free to expand, but not free to move in the Y direction. So that's my symmetry boundary condition there. In terms of rotations, I need to also make sure that they are fixed in rotations in the plane. So X and Z rotations will need to be fixed. So fix in X and fix in Z. So press OK on that. Now these are my symmetry displacement boundary conditions. The next thing to do is apply a pressure, and the pressure will be applied on the surfaces. I can select these two surfaces here. The important point here is that the surface normals are acting outwards. That's because of the shell's original surfaces were defined outwards, so it is shown at the surfaces here. So what I can do is if I apply a negative pressure there, I can ensure that the pressure is actually applied outwards. So I can see that the arrows are pointing outwards. So if I OK that, the pressures should be applied correctly. And you also need to make sure that all the surfaces in your models are consistently pointing the right direction, and also check the displaced shape and make sure that all the model is displacing in the correct sense. So these are the boundary conditions that are necessary to run this. If I go to Analysis and Studies, File, New Static, and Analysis 1, let's say Shell 1, and using constraint set 1, load set 1, and multipass up to 9th order with 5% convergence on local displacement, local strain energy, and global RMS stress. So press OK to that, and make sure you save your model before you commit to a solve and start the solution. Interactive diagnostics is fine, so this should solve pretty quickly. And it's finished in a few seconds effectively. It looks like it's managed to converge within 5 passes. That's fine, we can close that, and let's look at the results. So in terms of shells, stress is von Mises and deformed with undeformed overlay with element edges. Let's see what this looks like. I can see that this is deforming in the correct sense, so we can see that it is deforming outwards. That's fine, and maximum stress is 93 megapascals, and that is for a pressure vessel that is 10 millimeters thick. Another thing to plot there is the maximum principal stress, and that will correspond to the hoop stress, and these can be checked against, validated against the PR/T and PR/T2T calculations for thin shell theory. So these results look fine, but I've used the default mesh, so I can go back and improve my mesh. Let's do that. I can close this, don't save, and close that and refine my model. And in terms of controls, I can select the 2 surfaces I created, and let's make, say, element size maximum 20 millimeters. And if I do auto jam to create my mesh, I can see that it creates a couple of hundred elements, and even this is probably far too much refined for these high order elements. So we can close that, and yes, to save the mesh. We can rerun this model, but we can also go to define our optimization. Let's do a first run to make sure that the higher order elements, denser elements, work fine as well. So this is running. Again, finished in 3 passes, which is even quicker. And let's look at the results. The maximum principal, okay, and show, and that's 108 megapascals on the cylindrical portion, which is very close to even a very coarse mesh that we have started with. So 108 megapascals for 10 millimeter thick shell. So if we wanted to optimize this vessel, and if our design was limited to maximum von Mises stress of 150 megapascals, so if I plot the von Mises stress, maximum is 94. This is an over-designed vessel with 10 millimeters thick, and I wanted to do a design optimization. So let's close this results and then start an optimization study. So file, new optimization, and let's say call this study 1 with shell elements, and I want to minimize the total mass. So my design limit will be the von Mises stress, which is max stress von Mises over the whole model, and we can add that, and we can also add which variable to change. So that will be the thickness, and add that. So the current value is 10, minimum can't be 0, that will be undefined. Let's say minimum going back down to 2 millimeters. Initial value is 10, maximum value don't want to exceed 10 anyway, so we can say, so it will minimize the total mass, keeping maximum von Mises stress to 150 megapascals that I've defined here, and using analysis 1 shell 1 analysis with the load set I've just defined, and it will vary the thickness 1 variable between say 2 to 10 millimeters and try to optimize the geometry. If I look at the options allows me to choose an optimization algorithm, and I'll keep it automatic. Optimization convergence of 1% is fine, and 20 maximum iterations is fine. If the shape was changing significantly between optimization steps, we could take these, and it can remesh and repeat p-loop convergence. We can leave them out just now, and OK, and then run the optimization study. So the run is completed in a minute or so. You can close that and also look at the results of the optimization. And we can see that the thickness has converged to a value of 6.17, and the goal, which is the mass of the vessel, is 1.985, which is about 2 kilograms, and 2 kilograms is for a quarter of this half vessel. So for a 90-degree segment it's about 2 kilos, so for a 360-degree segment that will be about 8 kilos, and that will be similar to the 3D geometry we identified, or the 2D axisymmetric model that we have done before. In terms of design optimization, it's effectively converged within one iteration. So let's say close that, and we can look at some of the results on that. So if we do the review the results, we can plot the fringe plot of von Mises stress, and we can see that on the cylindrical portion the stresses are 150 megapascals, and we can also plot the maximum principal stress, and they are about 172 megapascals. Another interesting plot here, for example, let's say a measure like the mass, total mass, and how that changes in relation to optimization paths. So if you can show that, effectively shows that within one iteration it has managed to converge, and the mass is effectively 2 kilograms here, and this is plotted in terms of tons. So if we go back to our fringe plot, just again make sure we got the deformations in the correct sense. So if we go to fringe plot, quantity, stress, von Mises, display options, deformed, overlay, undeformed, with element edges, and then let's do an animation on that as well. And we can see that the vessel is expanding in the correct sense, that outwards. So this completes the Creo Simulate optimization of a cylindrical pressure vessel with spherical closures and closures, and we have managed to optimize this in a single iteration.